Greetings and welcome to a new video. In this video we will discuss a very important topic in linear algebra, is the singular value decomposition. We will see how we can use this for a specific matrix and decompose that in three matrices using this equation. Of course, we will see everything in the calculations step by step and also verify these in the MATLAB command window. Okay. This is the example we would like to discuss. Determine the singular value decomposition of this matrix. That's the objective. So how to work this out? Let's see that step by step in our calculations. Of course, we will use this formula later also to check that this is indeed correct. Okay, now step one is calculate the gram matrix. That means the following. You use the A transpose times A. So you need to transpose this matrix. That means the following. Transpose means you make your columns rows, or you can also say it in a different way, you can make your rows columns. So we see here 3 by 2 matrix, that will be then 2 by 3 matrix. That's actually shown here. So you see here that this is now here 2, 3, which is a row, now will be a column. 1, 1, which is a row, will be a column here in the second part, and we have here 1, 2, which is the third row, will be a third column. Now we also multiply by the A. Now we need to use the matrix multiplication, 2 times 2 plus 1 times 1 plus 1 times 1. That will be then in the first entry here, etc. This is just the ordinary matrix multiplication. That will be in this case 6, so you get the 4 plus 1 plus 1. The next one is then 2 times minus 3 plus 1 times 1 plus 1 times 2. That will add up to minus 3. And in the same way with the second row, that will add up to minus 3. And this second row and the second column here, we get 14 in total. Now we like to calculate the eigenvalues of this matrix, which is then the A transpose A. Now we use the formula for determining the eigenvalues of a general matrix. In this case, we have A transpose A. So we need to solve this equation. So the determinant of this minus the lambda times identity matrix will be then shown here. Now we need to work it out. That means that 6 minus lambda times 14 times lambda minus the product of these two. That's shown here. Okay, the next step is to work out the parentheses here. So you get 6 times 14, 6 times minus lambda times 14, and then minus lambda times minus lambda. Now and then you get lambda squared minus 20 lambda plus 6 times 14 minus 90 will add up to plus 75. Now we need to factorize this. That will add up to this one. So minus lambda minus 15 times lambda minus 5. Now we have here two solutions. Now in order to go with a singular value decomposition, it's important that you arrange your eigenvalues in the descending order. That means highest first and then make it smaller. In this case, we have lambda 1 is equal to 15, so that goes first, and lambda 2 is 5. So we cannot say lambda 1 is 5 and lambda 2 is 15. So it must be first the largest one and then make it descending. Okay, now we go to the step 3. We calculate now the eigenvectors. Now first we start with the lambda 1, which is 15. Now that is the same procedure as we have done in the previous video about the eigenvalues. We put here our A transpose A matrix minus now the specific lambda 1 times the identity matrix, and we will use a row reduction to calculate here the eigenvectors. So let's put it in. 6 minus the lambda 1. Actually the same formula here, but just lambda 1 and lambda 1 here. And minus 3 and minus 3 are exact same. This is then the 0 vector. Now we substitute here the lambda 1, which is in this case 15. So you will get here minus 9, you get here minus 1. So how can we make this second row zeros? Now that can be done by doing row 2 minus the third of row 1. So you get the third part of row 1 and do row 2 minus row 1. That is actually the situation here. Now you get here zeros, zeros. You copy of course your first row because you haven't changed that. Now you see here indeed what we wanted. We see here now dependent form in your system of equations. Now we can say the second column does not have a pivot. That means we have an x2, which is then a free variable. In this case we assign it just a t, and the t is an element of real values. Then we have, looking at this one, we get here minus 9 times x1 minus 3 times x2 will be 0. So in effect, we can say x1 is equal to minus 1 over 3 times x2. But since x2 is a t, we can also say minus 1 over 3 times t. Now taking all this together as a vector, you see it x1 and x2 in this vector, that will be then minus 1 over 3, 1, and you have also the t outside your vector. Now you can make this convenient by using a t that can be then get rid of this minus sign and this fraction. So you can say, let's make this eigenvector specifically v1, which is then the eigenvector of the lambda 1, by taking the t as minus 3. You can also take 3, doesn't matter. Then you have here a 1 and you have here minus 3. So it is more convenient to work with this eigenvector than this one. That doesn't matter. You can also do this. That will do the job also, but it is better to go for this format. Okay, in a similar form, you go for the lambda 2, which is then 5. Now you substitute here lambda 2. You can use this same equation. Now only changes the lambda 2. So you get 5 here, 5 here. This will be a 1. This will be a 9. So now again, you proceed such that you have here a 0. In this case, you see that row 2 is minus 3 times larger than the row 1. So you can actually say row 2 plus 3 times row 1. That will make this 0 and that 0. So you just copy row 1 and you make all these zeros. Again, the free variable is x2 because that's the second pivot. Again, in a similar case, and now you see here x1 is equal to 3 times x2, because if you go to the right side, so that will be then 3 times t. And now you get your vector in the general form using t. You get 3, 1, because that's the 3 for x1 and 1 for x2, and outside you have t. Again, we pick a convenient value for t. In this case, I think the t is equal to 1 is the perfect choice. So we get here 3 and 1, so we get now your second eigenvector. Okay, now collect now the result we have determined so far. We have here the eigenvalues, we have here the gram matrix, and we have here the two eigenvectors. Now we need to construct the singular value matrix. Now in order to do that, first we calculate the singular values. Those are the square roots of each of these eigenvalues. So the sigma 1 is the square root of the lambda 1. And the sigma 2 is the square root of lambda 2. So we have then square root of 15 and square root of 5. Okay. Now the singular value matrix, which is then given by this sigma, the capital letter sigma, is then given by this matrix. You see here now 3 by 2, which has the same dimension as the original matrix A. Okay, now the sigma 1 and the sigma 2 are in the diagonal, and if there is no anything else, we just put here zeros, and the other parts are also 0. So with this is now square root of 15, this is square root of 5. Now that's done, so we have our singular value matrix. Now the step 5 is construct now the right singular value matrix, which means the following, which is this V actually. So we need to have now here two columns, which has then v1 and v2. Those are the two vectors, but they're also normalized. So we need to make that also unit vectors. Okay, how do we calculate those v1 and v2 and then normalize? Now we first look at the v1s we have, that is the eigenvectors. And then this is the formula for going from the vector to the unit vector. So you divide by the length times the vector itself. In a similar form, you do that also for v2, so we have here 1, 3, minus 3, and now you do 1 over the length. Length is the square root of the square of this one plus the square root of that one. This will be then 1 over the square root of 10 times this vectors. Similar for v2, then you get the length of v2, and then you have also v2 itself. So again the same thing, but then for 3 and 1 each squared, and the square root of that one. Again, it is the square root of 10, and now you have your v2 in the unit vector. So that will be then in here and in there. And that's shown here. So since we have all 1 over square root of 10, we can take it out, and we have here our right singular value matrix. Okay. Now we need to construct the left singular value matrix. This is the most time consuming part. This is given by u, and this has a dimension of 3 by 3. We will see that shortly. We have here 3 vectors, u1, u2 and u3. Those are orthogonal and actually orthonormal, so they have actually unit values, unit vectors, and they are orthogonal to each other. So if you do the dot product, they will always result in zeros. Now we have the u1 and u2, so I mean we calculate our u1 and u2 shortly, but u3 still needs to be calculated using a different procedure. We will show you that in a minute. Okay, first the u1. How do we calculate that? That is given by this formula. So you do 1 over the sigma 1, we just calculated here, times the matrix given, which is here, and times the unit vector of v1, which is shown here. Now we go here, which is on 1 over the square root of 15 times the matrix given, times 1 over the square root of 10, because that was this one, times the 1 over minus 1 and a minus 3. Now, the two square roots can be also written as 1 over 150, the square root of 1 over 50. That's shown here. And if you multiply this matrix with this vector, you get actually the result here, 11 minus 2 and minus 5. You can also write this square root of in a different way. You can also say this 5 times the square root of 6. Why? Because it is 25 times 6. And the square root of 25 is 5. So you can take it out like so. And you can also proceed in the vector like divide everything by 5, so you get 11 over 5, minus 2 over 5 and minus 5 over 5, and you have this one. The only thing that is then left outside is then 1 over the square root of 6. Okay, in a similar form we do it for u2. This is, by the way, a unit vector, so it has a length of 1. Now this vector will be in a similar form, so we go proceed in a similar form like 1 over the square root of 5, because that's the sigma 2. And then the matrix A and also the unit vector v2. Again, we take the 1 over the square root of 10 times the 1 over the square root of 5 as 1 over the square root of 50 in front. And now we do the matrix times this vector in order to get this vector of 1 by 3 by 1. Now we can again look at this 1 over the square root of 50, which is actually 25 times 2. Again, you can take out the 5 as the square root of 25. And now you can proceed like 1 over 5 times 3, 1 over 5 times 4, 1 over 5 times 5 inside, and you get only 1 over the square root of 2 outside your vector. Now we need a third unit vector here. So we need to create a linearly independent set of 3 vectors. We only have 2. So the vectors u1 and u2 are linearly independent already and also orthonormal. So if you look at the length of them, those are 1, and also they are orthogonal to each other. So we call them orthonormal. Now we can use the unit vector, which is then here the unit vector in the z direction, 0, 0, 1, as a third vector for this basis we need to make, but this is not orthonormal or orthogonal for unit u1 and u2. So we need to make that also orthogonal to the other 2 matrices. So how do we do that? I mean to other 2 vectors. Now there's a procedure that you can use which is called the Gram-Schmidt process, and we only need to use the final step in order to go to the u3. So let's see that now clearly how we do that. So we already have the u1 and u2. Now we need to calculate the u3. The Gram-Schmidt process goes like so. So we create first vector, which will be then later normalized, but first that we call it w3, which is then our vector which we have chosen, e3, minus the dot product of this first vector times this vector divided by the vector u1 times itself, and this will be multiplied by the u1 itself also. So this is the general Gram-Schmidt process. We do that also for the u2, so you actually see with this one, it's that one is the exact same, the only change is just u1 to u2, and everything is also u2 here. Now we need to do here the dot products, here dot product, and also here, and then multiply it by the u1 here, and here by the u2. Now what is the result? Now you take over this e3, 0, 0, 1. If you do the multiplication here, this is pretty simple multiplication, because if you look at the U1 and E3, that will be then 0, because 0 times this, 0 times that, and 1 times minus 1 over square root of 6. That's why we have only this, because of this one. And then U1 times U1, that is just because it is a unit vector, it will be always 1. The same holds for U2 times U2, it is also 1. Now U2 times the E3, which is then this, again, the first two parts are 0, and you only have 1 over the square root of 3 times 1, which is then 1 over the square root of, 1 over the square root of 2. That's the only thing we have, and again you divide by 1, as we have mentioned earlier. Now you have your matrices, the vectors. Now we can proceed, because you see here a minus 1 over the square root of 6 times 1 over the square root of 6, which is actually 1 over 6. And you get a minus here, that will be a plus. In a similar case, you have here 1 over the square root of 2 times 1 over the square root of 2, which is then 1 over 2, effectively. So this goes, and it is now written in a more convenient way and an easier way. Now we need to calculate this, just vector here, another vector there, another vector there, so that will add up to this. You see here, we just process this 1 over 6 here, 1 over 6 there, 1 over 6 there, and you divide here everything by 2, and you calculate this. You have here now the results in the exact form. This is the W3, which is our vector, which is not orthonormal and also not unit vector. It's orthonormal but not unit vector. So we need to first make that a unit vector, and we call that U3. So we do that by 1 over the length of that W3 times the vector we have calculated. So we need to do this again, 1 over the square root of each element here squared. You see here everything is squared, and then times the vector W3 we just calculated. Okay, now this is, if you calculate that, it will be 1 over the square root of 1 over 3 times this. Now 1 over square root of 1 over 3 means actually the square root of 3, and if you process that here, clearly you get now this result for U3. Now that can be then put in here using also these two vectors, and now we have our U, which is our left singular value matrix. Okay, now taking the left U, the singular value matrix, or singular value matrix, and the right singular value matrix here together. Let's check that it is indeed correct, because we can use the formula and see if this is indeed correct. And remember, we need to transpose here the V here, so that is important. So we go with this matrix multiplication. This is U, this is the sigma, and this is the V transpose. Now for transpose, this scaling vector here doesn't have any effect, so we don't transpose this one, it stays the same. So we can put this 1 over the square root of 10 in front, and now we will process this matrix with this matrix. We have already made the transpose operation here, so 1, 3 is here, and then minus 3 and 1 will be here. So rows will be columns, rows will be columns. If you work this out, this matrix, I will show you this step. So you get here square root of 15 times 1, which is square root of 15, plus 0 times 3, which is this one. And same case with first row and the second column, that's the result. And then the second row and the first column, and the second row and the second column, that will be here, etc. Now if you work this out clearly, so this is pretty straightforward, I assume, for matrix multiplications, then you get the result actually as we have it in the original situation for A. So this is indeed correct. Okay, now let's bring everything here again, the eigenvalues in our Graham matrix, and we have here our 3 matrices for this decomposition. Let's now check this also with MATLAB. We have here now the definition of our matrix. You see here the matrix as we have given. This A tilde here means actually transpose, and then times A, that is our Graham matrix. And that was here 6 minus 3, 14 as we have it. So this is indeed correct. Now we calculate here the eigenvalues of this matrix, A transpose A, that is actually 5 and 4, 15. So 5 and 15. Of course, the MATLAB doesn't give it in the right order. It doesn't matter. We'll need to use it, of course, in 15 and 5. So lambda 1 and lambda 2. Now, next step is calculation of the singular value decomposition, for short SVD of A. Now that can be done using this command. You see here U, comma, S, comma, V in the brackets is equal to SVD and then parentheses A. That's actually this matrix. Now this matrix here, U, is the left singular matrix given here in the green box, which is this. Now if you calculate it for yourself, 2.2 over the square root of 6, that will be then approximately this one. This is of course rounded off. And you can go on for the other elements, over 9 elements here will be then this one. Now for the singular value matrix, that is the S, is the red given here, that is this one. So you see here the square root of 15 is here, 0, 0, square root of 5 will be there, 0, 0. Okay. Now the right singular value matrix, which is V, that's shown here. So we have here 1 over the square root of 10 times 1, that's shown here. Okay, now we can make the check also by ourselves by using U times S times the V transpose. So we have a tilde here, and the result is actually here. So you see here 2, minus 3, 1, 1, 1, 2, which is as we had it before. So we can say this is indeed correct. Alright, it was our example concerning the singular value decomposition of a matrix. We have shown the steps in order to go to the singular value decomposition for these 3 matrices. And we have also checked this using MATLAB. If you have any questions, comments, please let me know. I will try to answer them as soon as possible. See you next time in another video.